What up, mathletes? Let's talk about this today. Here's your warm-up. Go ahead and take a look at these graphs. I'm going to move this down just a little bit so you can see all the questions. Pause it if you need to, and I'll explain this in a minute. All right, now that I'm Starbucks charged, let's look at these graphs. Looks like Jamal went somewhere fairly fast, stopped, and then returned back. Aaron, wherever he went, he just went at a constant rate. And then Sophia, she really booked it and then immediately turned around, walked sort of fast back, stopped for a second, and then returned back wherever she started. The distance between A and B on Jamal's graph is constant. What does this mean? Well, between A and B, that means wherever he went, he stopped. He stopped moving, right? If he stayed at that location. Jamal's graph shows a distance of 0 at time C. What does that mean? Well, if distance is 0, that means Jamal returned to wherever he left in the first place. So he left somewhere, stopped for a minute there, maybe went to the grocery store or shop, and then came back home. Sophia's graph goes up more steeply than Jamal's or Aaron's. What does that mean? Well, that means wherever she went faster than Jamal or Aaron in the beginning. Describe Aaron's trip. Well, again, kind of like what I said earlier, Aaron left somewhere and walked at a steady rate the whole time. Did Jamal walk faster than Aaron? How do you know? Well, I know he did walk faster than Aaron, and I know that because his graph is steeper, a steeper graph. So he covered more distance over less time, which means he walked faster, or ran faster, rode faster, whatever he did it faster. Awesome. Let's roll. Shapes of graph is what we're talking about today. So we're going to be looking real in-depth at graph today and more specifically on the next lesson. So every 4 years, FIFA International hosts the World Cup. I know it says Federation Internationale de Football Association, that's FIFA, hosts the World Cup, which is the most widely viewed sporting event in the world. If you want to know when the international soccer tournament occurs, you can look at how many people searched for the term World Cup each month over the past decade. Although the number of searches has several peaks or relative high points from month to month, the graph shows the sharpest increases every 4 years. Specifically in 2006, 2010, and 2014, which are the years that the event has been held. So we're talking about, look here. So from month to month, you see relative peaks of the search, but woo, every 4 years, you see that peak just shoot up. And why is it doing that? Because that's showing you when the event is being held. So it makes sense that when the event is being held is when more people would be searching for information on it. So that graph is actually helpful in telling us when the event is. All right, so vocabulary today, we actually have a few vocabulary, or 4 of them. We have line symmetry, which is a figure has line symmetry if each half of the figure matches the other side exactly. It is increasing where the graph of a function goes up when viewed from left to right. So again, math, we read like a book, just like we do when we're solving math problems, from left to right, correct? My video up here is a mirror image of me, so when you saw me doing this, I was going from left to right from my perspective, but this is a mirror, so I got to start over here and go, or over here and go, so I got to go right to left for me. Anyway, if that doesn't make sense, ignore it. Extrema. Oh, by the way, when is it decreasing? When it's going down from left to right. Just like you should know, a positive slope is going up from left to right, and a negative slope is going down from left to right. Okay. Extrema. These are points that are the locations of relatively high or low function values. So we have relative highs, relative lows. We'll explain that mostly in the next day's lesson. And in behavior. In behavior is not just looking at the left side of the graph. It is looking at both what's the function doing at the left, or at the right, excuse me, and what's the function doing at the left, right? So it's saying at both ends of the function what is happening. We're looking at the behavior of the graph. Okay, write those down. Let's roll. We're going to start with really talking about symmetry. So let me go ahead and zoom in just a tad. some of my stuff out of the way. The graphs of some functions exhibit a key feature called symmetry. A figure has line symmetry if each half of the other figure matches the other side exactly. So let's look at these. If we have symmetry in the y-axis, let's look at this. Notice this is a parabola. That's what this is called. This shape is called a parabola. It looks like an N, or if it goes the other way, it's a U. And this is one that has symmetry in the y-axis. So if I use that y-axis as a mirror, the right side matches perfectly on the left side. But you need to understand, it isn't always directly on the y-axis. For example, we see this shape should have symmetry, but it's going to be to the left of the y-axis. It still has line symmetry, because if we go over to x equals -1, what happens? It has a perfect line of symmetry that the right side matches over onto the left side, or vice versa. So, can the graph of a function be symmetric about the x-axis? Well, let me talk about that. We had symmetry in the y-axis right there, or just a little bit to the left of the y-axis, or we could have it to the right. But could I potentially have, like, what if I have this? I bet you're thinking, oh yeah, this has symmetry right down here. Here's the problem. Are you ready for the big problem? It says, the graph of a function. Anything that has symmetry in the x-axis is not a function, because it is going to fail the vertical line test. So no, a graph of a function cannot have symmetry in the along the x-axis or any line, horizontal line. All right. Might need to zoom out here, but let's see what happens. Okay. Oh, yeah, we're going to zoom out here. We're just going to talk about line symmetry. So let's look at these functions. I'm going to move me up and out of the way a little bit. See this function f of x equals -3x plus 8? Doesn't matter where I take this horizontal line right here. The right side will never match over onto the left side. They're opposite. Okay, so no, this doesn't have line symmetry. Oh, didn't mean to do that. I hit the wrong button. Pardon me. And we're back. Let's go to the next function. G of x equals -x squared minus x plus 12. Well, check this out. If I move my line of symmetry to about right here, which looks to be almost x equals -0.5, what do we see? We see the right side would match perfectly over on the left side. So yeah, that has line symmetry. G of x does. How about this function? Yeah, I can cut it in half right here at x equals 1, and the left and the right side will match up. Oh, no matter where I put this, it's not going to match up because we have a weird oblong shape there. This one can be tricky. A lot of people would put it about right here and say, hey, those are like just opposites of each other, right? Well, yeah, but the problem is if I mirror this over here, right, it's going to match up down this way, and this side would match up this way. So no, it's not symmetrical. It doesn't work like that. Okay? They have to be mirror images that overlap onto each other exactly. And last but not least, let's look at this v. It's an absolute value function. You know absolute value. Whenever it meets at a sharp point, it goes up like that, or even up to down, it's an absolute value function. Just so you know, that's one of the ways you know what it is. And yeah, this v has perfect symmetry here. What, x equals -3? Perfect. All right, now we go to the next resource. We're going to talk about symmetry still, line symmetry. So use the graphs to describe the line symmetry, if any, of the functions. Yeah, let me look at this one right here. I can see clearly there's a line of symmetry that goes down right here. What is that? That's at x equals 4 right there. So that is the line x equals 4. And that is line symmetry. So what are we going to say here? Symmetric in the line x equals 4. Boom, right there. Yeah. How about right here? No, there is no straight up and down line I can draw, so no line symmetry there. There you go. Awesome. Is there anything we want to talk about? Nope, just answers. So let's go ahead and reset this for future. All right, as we move on, this will be our last example for today. Maybe you'll get some homework time, we'll see. So let's look at this stream right here. Do you see how this is making a perfect parabola? Gravity works great that way. So let's go down and see what this means if I were to look at this graph. Now notice there's certain areas of this that are kind of dotted in. It's because if you can continue the graph, first of all, this is where the fountain starts spraying. Theoretically, this represents a parabola that would continue this way, but it really just starts in reality here, and it ends at the height of 0 right here. But theoretically, if we're talking about just a parabola, there's a parabola that goes through this that goes on for forever down. Okay, fountain is spraying a stream of water into the air. The graph represents the path of the water, where x is the distance from the fountain, and y, there we go, I can see that better, and y is the height in feet of the stream. Find and interpret the symmetry in the graph of the function. I should get my glasses on so maybe I can see. How about that? The right half of the graph is a mirror image of the left half in the line x equals -2. And we can see that. I can draw a line right here at x equals 2. And that is my line of symmetry. Okay? And here's what else I see. Starts about right here, just somewhere almost right about a height of 5. And that's exactly 2 feet away. So that's 2 feet away. That's from 0 to 2. Okay? Well, if I travel same over here, we notice that in another 2 feet, or 2 whatever unit we're using, the height is going to be the same. That's like if we were looking. So in the context of this situation, what we know is the symmetry of the graph tells you that the height of the stream of water when it is from 0 to 2 feet away from the fountain is the same as the height of the stream of water when it is from 2 to 4 feet away from the fountain. Okay? That's what this symmetry tells us. So let me go up top again, and we can kind of look about that in terms of the video. See this stream right here? So if I'm looking at this, let's see, let me use a nice little red mark. So we were saying this is 2 units away, okay? And that height is the same as this height if we go another 2 units over. The height is the same right here. That's what we're talking about. That's what that line of symmetry is telling us about this stream of water. Awesome. Find the maximum height of the stream of water. Well, the maximum height is right there in the middle where that line of symmetry hits at x equals 2. There's another thing we know from this graph. Right. Actually, that was it for today. We're done. So with that said, peace out.